Hello everybody, it is now 2:30. It is time for our next project. This one is by Juan Vasquez, Dan Kubik, and David Bumpus. The project is 3D environmental mapping and imaging for AUVSI. The advisors are Dr. Sanchez and Mr. Schmidt.
Thank you, Garrett. As you said, our project covers the topic of three-dimensional environmental mapping and imaging for the AUVSI Roboboat. I'm Juan Vasquez. My partners are Dan Kubik and David Bumpus. Our project advisor was Dr. Jose Sanchez, and our client was Mr. Nick Schmidt. So here's a brief overview of what we're going to discuss during the presentation. And the first area that I want to focus on is the background of the problem. So since 2013, Bradley's competed in an international roboboat competition. Now what this competition requires is that teams design an autonomous boat that must perform a variety of tasks. Now what this essentially means is when the boat is placed in the water, it must not be interfered with by teams. It must be able to make decisions without any interference. So, as I previously mentioned, it must perform a variety of tasks. These tasks revolve around obstacle detection and obstacle avoidance. And a problem that Bradley teams have specifically been having in the past is with determining how far away distances are relative to the boat. Now, because of these distance miscalculations, there has also been an error with navigation overall. So if you notice in figure 1, the boat is usually supposed to follow the black designated path, but because of those distance miscalculations, a lot of times it'll veer off in different directions, which is shown by the red arrows. Also, in figure 2, you can see a first-person point of view of the boat's directional pattern and its decision-making process. So aside from mitigating those navigational errors, the team may also want to isolate specific areas of interest. And that can be seen with the designated yellow oval. Now these areas of interest can range anywhere from buoys on the water or specific objects on the water. And we want to be able to give the team a desired range that they can focus on. Now, this project was geared around a certain amount of objectives. The first was being able to measure that surrounding environment of the boat and the objects. We wanted to do this using what's known as a Lidar technique. And we also wanted to be able to operate in real time due to the fact that this is a time-based competition. And lastly, we wanted the configurability of this system to be as simple as possible, not only for the boat team that's going to use the system, but also future teams that will develop upon our project. So, as I previously mentioned, we want to use a Lidar technique. Now what that essentially is a surveying technique similar to radar, but that uses light pulses, or light lasers, sorry. And basically what I mean by that is it sends out light pulses from the origin onto the surrounding environment objects and measures the time that it takes for those light pulses to hit those objects and then return to the origin. And by doing so, we're able to find out the overall distance of those objects. Now, this technique is growing in popularity in the autonomous vehicle industry, specifically for its ability to reduce the amount of human error that's involved with driving, and therefore reducing the total amount of accidents that are also involved. The next section that I want to focus on is the functional requirements that we adhere to for our project. So we had a variety of functional requirements. The first that we wanted to follow was being able to obtain and store LiDAR data, those distance measurements of the surrounding environment. Aside from that, we also wanted to obtain camera images and add an extra dimension of color to the surrounding objects of the boat. We also wanted to reduce the LiDAR data set as instructed, and what we mean by that is being able to take a user input of a specified range, as I mentioned earlier, and get rid of any unwanted data, so to focus on those areas of interest. Aside from this, we wanted to create a color overlay image representing distance, and this is best represented in figure 5 shown here. As you can see, the lighter colors are representative of distance that's farther away. So the light blue can be shown more or less with the wall, and then the darker colors are more representative of closer objects, such as the chairs, as you can see with the purple. Now, one of the last functional requirements that we wanted to focus on was determining the nearest object and location of those objects relative to the boat. Now, with that being said, I'd like to focus on the overall overview of our project. Now, there's three main areas of focus, or processes, if you will, for our project. The first is data acquisition. Now, what this involves is taking in all of the incoming information of the boat's surrounding environment. This involves two main components. The first is the laser scanner and the incoming Lidar data packets from that laser scanner, those distance measurements, and the camera with its produced image. Now, the second section involves data selection. So taking all of that acquired information and then formatting it in a way where it's useful for our third section, which is data processing. Now, what this involves is formatting that selected information to adhere to our functional requirements that I previously mentioned, and those will be designated as our outputs, as you can see. So now I'd like to talk about how we were able to divide those three processes amongst our group members. So we were able to use a captain designation for our overall project, and what that means essentially is that we wanted to split each individual process amongst a team member and have them be a captain of that process. Now, what that means is they are in charge of the overall part of that process and its completion. I myself was in charge of data acquisition, Dan was in charge of data organization, and David was the captain of data processing. Now, the next section I'd like to focus on is the development of the data acquisition, that first process. So this section involved two main components. The first being the laser scanner and receiving those incoming Lidar data packets, and the second being that of the camera and being able to produce an image using the embedded device. So initially, when I first started this project, I wanted to develop an environment that was following a couple of different factors. Now, this environment or operating system, if you will, had to adhere to three different factors that were my main selection factors. The first was the overall size of the operating system. We were limited to overall disk space, and I'll mention that a little bit later. So I wanted something that wasn't that large, because obviously we had to create programs as well. And software availability, I wanted something that had a little bit of a larger community base, just in case I ran into any issues. And configurability was also a big concern, because I wanted to be able to install the operating system with ease and have it be simple to use. So what I was able to choose was Ubuntu Server, which was an operating system that it's a Linux-based operating system that's terminal only. So it's very small in size in comparison to a lot of larger graphical interface operating systems, graphical user interface. And also, it has a pretty large community base because it is Ubuntu and it's a pretty big name. And the configurability behind it, I'm able to install this directly and boot it onto the embedded system within a couple of minutes. So it was ideal. Now, with that being said, once I was able to choose an operating system, the next section that I wanted to work on was being able to boot that operating system onto the embedded device. Well, there were two main options that I looked into. The first was a micro SD card, and the second is an embedded multimedia card. Now, we ended up, for our final product, going with an eMMC because of its ability to boot faster onto the embedded device. However, it should be noted that for most of the project, I used a micro SD card because of its larger size in comparison to the eMMC. I had about 16 gigabytes with the micro SD card, where the eMMC was only 8. So after I was able to fully install an operating system, I then wanted to focus on establishing network connection for that operating system. This involved, the reason that I wanted to do this is because I wanted to have an up-to-date operating system. I wanted to be able to upgrade all the programs that we were using, and I also needed it to download certain function libraries for program interface. Now, with that being said, after I was able to establish internet connection, have a fully functional operating system, I then began working on interfacing the camera. Now, one of the first steps in interfacing the camera was being able to detect that camera on the embedded device. Now, I was very happy to see that I was able to just connect the camera and have it be detected due to the fact that our webcam that we chose already had a pre-installed Linux driver, which means that I didn't have to worry about that at all. So once we were able to then detect the camera, I moved on to picking a functions library or a program that I would use for the actual image capture. Now, I ended up choosing open source computer vision, which is a Linux supported C++ interface function library. And those first two reasons were part of the reason that I chose it, but also because of its ability to be geared towards video capture and image registration, which are not only big towards the data acquisition side, but also play a major role in the data processing process. So once I was able to pick a functions library, I then began working on the program in and of itself. So the functionality of the actual camera interface program, the way that it works is that it is always capturing live video. So the webcam is always running once you run the program. But with that, it's continuously capturing snippets from that video and overwriting them. So it's taking still images from that video in spans of 3, and once it gets to the third photo, it then overwrites the first image. Now I store these images in a portable PixMat format, which is just a basic image format. So once I was able to fully interface the camera, I then began working on interfacing our VLP16, which is our laser scanner. In a similar manner to what I did with the camera, I wanted to first start by finding a functional library that I could use for the process. I ended up going with a library known as libpcap, which is used for Ethernet detection. This was ideal because the VLP16 only communicates through Ethernet, so I wanted to find a way to work with that, obviously. And the actual method that I used for detection is known as user datagram protocol, which is an Ethernet detection method. The actual functionality of the program works by the laser scanner is always continuously scanning 360 degrees. So as it does that, the embedded device is able to pick up those packets coming through representing those scans, each individual packet, and then store them into a text file on the embedded device. So each text file is representative of one data packet. Now, one of the last sections that I worked on was reducing what's included in those data packets. Shown here in the overall image is an overall data packet. Now, as you can see in the red designated section, that is all unwanted information for the next section. It includes a lot of header information and just unnecessary information for our side. For the next section, So what I had to do was reduce that overall size, reduce that overall packet to just what's included in the green section. And as you can see, it starts at the starting address FFEE, and really the only information that's included in this section is the data payload, or those distance measurements relative to the boat. Now with that being said, I want to pass it off to Dan Kubik, who's going to discuss our data selection section.
Thanks, Juan. So now I'll talk about, as he was saying, the data selection section or data organization of that data that he has now just acquired. So as you can see by the block diagram, my work is primarily focused with the embedded device. Working towards those functional requirements that we're hoping to achieve, I really had two main goals in mind. First, I wanted to take the data from these Lidar data packets that Juan is creating and extract that data and put it into a form that's easy to understand and use when we actually do processing in the later stages. And then second, I also want to be able to create this image with a color overlay that can represent that distance information by when you look at it very quickly. Now, the way that the laser scanner works is it uses what's called spherical coordinates to identify the location of where data points are located in space. To do that, it uses the actual distance from the observer to that data point, as well as two angles, which you can see in this image, the azimuth and the altitude. Now, inside the actual scanner, there's 16 lasers that all point in that same azimuthal direction, which then basically spin around that blue vertical axis. And each of those individual lasers are picking up individual data points as it spins around. Now, when I get the data from Juan in these data packets or these text files, they always start the same way. As he was mentioning, it always starts with 2 bytes of information, the FF and EE. And then it's followed by pieces of information that correspond to those individual laser data points. There will be pieces of information like the azimuth or the distance and reflectivity points at those individual data points. Now, again, this is how every single text file starts the same way and contains the same piece of information, but we're getting a lot of these from Juan. Now, This slide looks really confusing, and that's actually kind of the point. What I'm trying to get across is that inside of this blue box, this is what a data packet contains. It's a lot of information, and really, even though it seems like a lot, which corresponds to each of these individual points, going around that full circle of the laser scanner's rotation, each of these data packets really only corresponds to about 1 to 5 degrees around that full circle. So to get enough information to be visually meaningful, we really need a lot of these packets. So it's really important to organize this data as we're getting it in so we can use it in a useful way later on. So to organize this data as it's coming in, I created basically a hierarchy of classes in C++. At the lowest level, I have what's called the data point, which contains information at the individual data points acquired by those individual lasers. So it contains a piece of information like that distance or the reflectivity measurements. And then as you move up the hierarchy, basically the higher levels contain elements of the lower levels. We keep moving up, adding more and more pieces of information. The biggest takeaway here, I guess, that the highest level is what I call a master block, which again contains elements of all the lower levels as well. Now, the master block is special in a way because it also contains elements of logic that help decide whether or not we want to keep the information as it's being sent in. The idea is we initialize one of these master block objects and send it this stream of data packets that are being generated by WAN, which the master block determines, do we want to keep this data or not? If we do, it's because it falls within 2 regions, either the frontal region in front of the boat, which we'll use for that additional registration or creating that color image, or for a selection range, kind of like in this image here, where we might have a region off to the left of the boat or another area of interest that the boat's control system might want to look at in particular. So to kind of visualize how the data is going to be flowing, we always get 2 angle inputs to define that selection range from the boat's control system. And then from there, we use those 2 angle inputs to initialize this master block object so it knows what to look for. At that point, we start sending it the data packets from WAN, and it determines whether or not we want to actually keep that. It keeps filling it up, keeping track of how much data we're actually sending it. It'll take up to 300 of one full sweep basically around that circle, and after that, it won't take any more. It'll consider itself done. At that point, we basically have a snapshot of time of the data around the boat, right, which we can then use to create the color image. We can register it with the camera image and do further processing that we want to do with that particular data. At that point, then we loop back and we create a new master block image with a new selection range, and the process keeps repeating. Now, this slide demonstrates that the master block does actually receive and collect data as we expect it to. It's a picture of a box, as you can see from our scan. In the bottom left-hand image, this is what we expect the data to look like. This is a screenshot from the software that comes with, our laser scanner, and this is again what we expect that data to appear to look like. In the bottom right-hand image, this is the decoded information from these text packets as stored in a master block object, where we selected the range to just show the box. And as you can see, they are the same data set, and the transfer was successful. Similarly, in this image, you can see that selection range in effect. In the top left-hand image, this is a full 360-degree view of a room, zoomed out kind of. In that circle, what you're seeing is basically where the center of that circle is where the laser scanner is located. That circle itself is data points it's picking up off the floor around it. Now, if we want to look at this 180 degrees in front of the laser scanner, what we can do is we can actually filter out the bottom half of the image, which you see in the top right. And you can see that the circle is now a half circle and the bottom of the image has been removed. It's no longer stored in that actual master block object. Similarly, we can pick really any other range. Like in the bottom, I decided to choose 90 degrees. And you can see it again, it sampled it down, so we really removed all the excess data that we're not interested in. And then finally, the last main functional requirement that I hope to achieve is creating that color overlay image. The idea is that we have the LiDAR data, and we're going to create this 2-dimensional image that has those colors like Juan was demonstrating with. When you look at the colors, you can quickly tell how far away things are in that area. I guess 2 big challenges to create this is, one, how do I go from the 3 dimensions of this LiDAR data down to the 2 dimensions of this picture? And then 2, notice that in the LiDAR data, there are gaps in between the data. That's because of the spacing of those individual lasers. So for our final picture, we don't want those gaps. We want to have hopefully a smooth picture if possible. The solution that I found to achieve this is what's called Barnes interpolation. It's actually an invention. It was invented in the 1960s to create weather maps. The idea is you have unevenly distributed weather stations across the country where we do know the temperature, or in our case, we do know the actual distance information at those points. But we want to fill in the gaps in between of places where we don't know. The Barnes interpolation method, it's like a weighted average. It compares the actual distances to the actual the distances of how far away it is to the actual known points. You might be wondering, well, it looks like the Barnes interpolation is in 2 dimensions. Again, we have it in 3s, and you're right. So the way I decided to make it down from 3 to 2 dimensions is I converted from spherical to rectangular coordinates. And what I decided to do was compress the data so it's really only in that z and x plane. So really we're interpolating over that kind of snapshot of the data. And what the values that I'm using is the actual distance information. That's what we're interpolating. Now, to test this Barnes interpolation, make sure it's working correctly, we put the laser scanner on that chair in the lobby of the Renaissance Coliseum, as you can see. And again, this data set is kind of what you're seeing there. Here in the circles, you can see these are the 3 columns that are kind of out there. And then also notice we have pieces of foam that we put on the floor that kind of would represent what a buoy would look like out on the water. And again, you notice that they're both in the LiDAR data, so it did pick it up by the scanner. Now, when I run the Barnes interpolation, I created a range of 9 different colors, green being the closest and this kind of maroon color being the farthest away. And visually, it's kind of exciting because you can, when you know what you're looking for, you can clearly see that in orange, here are those 3 pillars again. Here are the 2 buoys, and you even can kind of tell there's the shape of the ceiling. The stairs did get a little jumbled, but for the most part, objects that we would want to see out in like a lake, which are very defined, are clearly seen in the Barnes interpolation picture. Now, I did want to verify to see that the math and the actual interpolation values were correctly calculated. So what I did was I measured the actual distance to the pillars and the buoys and wanted to verify to make sure it was assigned the correct color identification that we'd expect. The pillars and the back wall and really are what you'd expect them to be. They're in the correct range. The only exception is the left buoy was off actually by a significant margin. We would want it to actually be, so you can see it's 7.87 meters out, which would put it in that blue category, just like the right buoy, but for some reason it put it in the green category, which is almost nothing. I'm not 100% sure why this is, especially since the rest of the interpolation was correct, but I suspect it might have something to do with that, remember that circle of data that I was picking up from the floor? I think it might have been weighing it down towards that one particular buoy, which thrown off that particular calculation. And with that said, I'll pass it on to David, and he'll talk about, again, how we did extra processing on that data that was acquired by Dawn and then organized by myself.
Thank you, Dan. So I'll be discussing my work thus far, and it primarily consisted of developing those 2 outputs that we've been referring to. The first primary responsibility that I had was detecting the nearest object location and then passing the distance to that object and the angle to that object to the boat's navigation. Then also I worked along with Dan to work towards a solution for registering or matching the Barnes interpolation you can see in this image with a webcam image so that objects in the image had implied distance and were directly matched to those objects. And so I used the scale invariant feature transform for both of these tasks, and it's an algorithm that is implemented using OpenCV or open source computer vision, which is the library that Juan had used for the image capture from the webcam. And so really there's a major strength with the scale invariant feature transform or the SIFT algorithm. And as the boat is rocking in the water, there's going to be some rotation in the image. And so we need an algorithm that's robust against these changes and that's still able to detect objects in images, even though the image may be changing in its shape or appearance. And so you can see in this image that the woman's hat and her nose are able to be matched, even though the size of the image has changed. So as the boat moves closer and further from objects, the size and appearance of those objects is going to change. And also as the image is rotated, you're still able to match certain features of the image. So this is a 5-step algorithm, and the first step in the algorithm is what's known as scale space extrema detection, and it's described there in figure 39 visually. And what it's showing is it's all the same image at different levels stacked on top of each other there. Those are coordinate grids of the pixels for that image. And so we're applying a Gaussian blur to the image. So we're blurring the image, and we're subtracting that blurred image from the original image, which produces then that output that describes the contrast or the changes, or the regions in the image where changes in color are occurring. And so this allows us to detect the edges of objects and use those to find our key points. And so anytime where there's an area in the image of high contrast, that's the location of a potential key point. So this is another description of how we're adjusting the scale, or the sigma value, or the standard deviation for that Gaussian blur. And so as we increase the blur for the image, it influences how the key points appear, or how the contrast appears in the resulting image. The second step in the SIFT algorithm is what's known as key point localization. And so we have a list of potential key point locations from the first step, but we want to reduce that set down to only the highest contrast key points and the most valuable key points. So we threshold that and remove low contrast key points. And then we also eliminate key points that occur on the edges of images, because these aren't useful for object detection and are often found in error. So after this, what remains are just the strongest key points. And so far we have key points that have a location within the image, and they have a scale, that's that sigma value or standard deviation from the first step. And now we want to determine the orientation of that key point. And so how has the key point been rotated, or how has the image been rotated from the original image to the current image? So we calculate the gradient and magnitude of the color at each point, or at each key point in the image that we're interested in, and that's how we assign an orientation to the key point. In the fourth step, what we're doing is we're assigning a key point descriptor to each key point, and this effectively serves as a fingerprint for the key point, where we can identify each individual key point because it has an array of those gradient vectors, or many of those gradient vectors that act to identify the descriptor for that key point. And so we can search through the image key points and match those key points to similar key points in other images. And that's step number 5. So this is a visualization of my implementation of the SIFT algorithm using OpenCV for an image in the lab. And you can see the key points there are shown as red circles. And then the center of those key points is the location of that key point, or the center of those circles is the location of that key point. And those key points often occur at high concentrations around objects. And so this is useful for object detection. So after I implemented object detection, or key point detection for images, I implemented object detection for point clouds. And so using something similar to OpenCV called the point cloud library, which is also open source and has an adaptation of the SIFT algorithm, I was able to implement the SIFT algorithm for Lidar data. And the key points here are shown as blue spheres. And again, they're occurring on the edges of objects. However, there's a slightly different meaning for the key points. So when, for an image, we're comparing the changes in color, for this point cloud, we're looking at the changes in distance. So it's still detecting those objects by looking at the edges of those objects where distance is changing, but there's slightly different meaning. And so with this, I was able to determine the nearest object location by calculating which key point was located closest to the sensor, and using that information and that coordinate location, calculate the angle and distance to that object. And so this was accurate up to 95%. And so to conclude, what we've discussed today, Juan has been responsible for the data acquisition and Lidar Ethernet detection and image capture component of our system. Dan has been responsible for the data storage and organization of our data, and also worked along with me to develop that depth overlay for the image. And I myself have been working toward the data processing and detecting the nearest object and passing that information on to the boat's navigation system. And so two of the main difficulties that we faced in this project were difficulty acquiring the data packets, and the speed at which the data was coming into our embedded device exceeded our ability to process that data, or to read that data. And so there was missing data information as we were reading the data. And the second problem we faced was that lack of precision in the Barnes interpolation that Dan discussed. And so we don't necessarily have a reason for that, but it was one of the major problems we faced. And so then going forward, something in the future that we would think would be possible to implement would be registration of the Lidar data directly with the image data. So this is a hypothetical depiction of what that would look like, where the yellow lines correspond to the matches between key points in both sets of data. There's difficulty with this because of the difference in meaning between the two key points, because in the image we're looking at changes in color, while in the Lidar data we're looking at changes in distance. But that's something in the future that could be worked towards. And so overall, we've been able to successfully interface the camera and laser system with the embedded device, the Odroid XU4. And we successfully detected the nearest object location and distance to that object with 95% accuracy. And then finally, we were able to generate a depth overlay that clearly defines objects within the data and within the environment that are useful for detecting how far away those objects are. And so that concludes our presentation today. I'd like to invite my partners up and take any questions you might have. Yes, Tim.
I got 2 quick questions. Slide 19, if you wouldn't mind going to. Okay, yeah. So you say you're storing this picture in a portable PixMap format. What was the decision behind that, or compared to something like a JPEG or a PNG?
Yeah, so I have all those comparisons actually up here right now. Portable Pixable format is the lowest common denominator color image file format that you can get. The reason that I chose it was because in comparison to some formats like JPEG, compression is permanent for JPEG, right? So portable pixel format, really the main reason right now is in case a future team wanted to compress that format into another format, it's relatively easy, whereas with JPEG you wouldn't be able to do such.
Okay, and then my other quick question was, so you have a LiDAR and you have a camera. And you talked about how SIFT would remove issues with like tilts and stuff. Was there any issue, I guess, with how the cameras have to align? Is there a certain way you have to have the camera compared to how the LiDAR sits?
No, so with the registration, as long as similar objects are located in both data sets, it doesn't matter the orientation of those objects. And so that was one of the strengths of this algorithm, was that their position relative to one another doesn't matter so much as how the key points are being obtained within that algorithm.
Thank you.
Yeah, I have a question for Juan. You chose Ubuntu for your operating system for the boat. I've often found that Ubuntu can sacrifice efficiency and speed in the name of ease of use. In your opinion, would it be like come competition day, would performance be better using like a more stripped down Linux distribution like Debian, or even as far as Arch or something like that?
As far as the selection for, I did have a comparison between server and desktop. It really just came down to the overall size of server, and that in combination with the, I see what you're saying, but it also mattered with, like I said, the software availability. So the Odroid XG4 is a really new embedded device. I had to find a platform that I could use that was compatible with that Odroid while also still being small in size. So I have looked at Debian, and I even looked at building my own kernel, but then the problem really became how much time it took to do so. So for a while I was working on building a kernel, and I wasn't able to fully complete that, but yes, that would be ideal for the faster processing.
So you're saying it wouldn't necessarily be worth the added complexity, but would you say maybe leave that open for future teams?
Yeah, I would definitely say to leave it open, but for this project, I wouldn't say it was necessary.
Okay, so you are using spherical coordinate system, but you are trying to convert it into Cartesian coordinate system. As our distance increases, small angle change will create big increments in x, y, z. How you are going to handle it? Because of such issues, you have to limit the, I guess, range. You guaranteeing certain accuracy. Any idea about that?
That's true. I think, well, you're right. As the distance increases, you're right. I think the accuracy would decrease. When I created when I got to that point in the project, it was later in the semester, so I did take that into account, but we haven't offered any solutions for that particular point in time yet. But you're right. I think if we would add more time, there would need to be some way to look at that. Kind of for the.
So one potential thing that can be done is, because it would be a non-uniform transformation between the LiDAR point cloud in 3 dimensions and 2 dimensions, like you're saying, is to register the 2-dimensional image that is produced with another data set. And so if we could directly register the different elements of the image or the LiDAR point cloud with one another, that would have, it would enable us to have a non-uniform match between the 2 data sets. And so that may help to reduce that error some.
I guess another, I want to mention too, that I don't know how far it would be to affect that. We would probably need to do more testing to see how far of a distance would be inaccurate enough that wouldn't be good to visualize. But the back wall was about 13 meters away, which I think for the aspect, for at least for the boat application, I think is significantly far enough to identify objects on the lake. If it was becoming a problem, we would obviously then come to AUVSI to address it. But for now, I think it might be okay.
Another question, probably I asked this before during your preliminary presentation. This is meant to be used for boat, and boat will be on the water, and the water, maybe there may be some motion. And how are you going to compensate such motion? So the camera feed may be not consistent with LiDAR reading. How are you going to compensate those?
Yeah, so that was one of the reasons for selecting the SIFT algorithm, because the images and the data is changing its orientation. We need an algorithm that's robust against those changes, and so as similar to the question Tim asked, the relative position of objects within the image doesn't matter. They can be moving within the image. You're still able to register those objects because you have the actual object itself is being detected, not just a position within the image, if that makes sense. And so we're still able to detect key points, detect objects, even though the image has been rotated because of rocking that the boat experiences in the water or motion throughout the challenges.
Are there any further questions? All right, well, thank you.